Alright, so we're back to computing the matrix equivalent to quick select, and we just finished with part A, so we now have a way to compute the number of elements between two other entries in the matrix. And now what we want to do for part B is to create a sampling function. So essentially we want to pick an entry of M that is between entries mi naught, j naught, and between I1, j1. We want to pick such an entry uniformly at random. Now there's a really simple way to do this. So we can essentially associate with each entry of the given form a number. So in particular, we know that the total number of such entries, so the total number is between 1 and Tn, where Tn is what we computed in our algorithm before. So if we just associate each entry a unique number between 1 and Tn, so that each individual entry gets its own number, then there's a one-to-one correspondence between the entries and these numbers. So then there exists a one-to-one correspondence, or a matching, a labeling, whatever you want to call it, between numbers in the range 1 to Tn and the matrix entries. So if we pick some number n, or let's call it z, so if we pick z uniformly at random from 1 to Tn, then this is equivalent to picking the matrix entries uniformly at random. And this is just because once we pick the number, we can just output the associated matrix entry. So we're allowed to assume that we can pick from a range something uniformly at random. So we'll use that procedure and then output the associated matrix entry. And that gives us exactly what we want. So the only thing left is, so this works for any possible association that's a bijection, so it labels each entry exactly one of these numbers. So the question is, can we compute such a labeling efficiently? So now how do we compute such a labeling? So now I'm using the phrasing labeling as the number that we associate to an entry. So the way we're going to do this is just by doing part A again, except now we could create this labeling, and let's let it be an array. So we have this, and we're going to let L1, so the thing with the first label is just going to be S1. Then we'll let L2 be S1 plus 1, etc. So essentially the order that our algorithm computed, so when we did our algorithm, we went through each entry of this form. So we're just going to go into the same order. So in particular, if we have a row, it has some sk to lk, assuming that there exists entries of the form in this row, so assuming that sk is at most lk, then we're going to let the labeling be exactly the total number of entries seen so far and keep going. So we let TK be the number of entries of the form we care about seen before row K. So let's make it -1, so it's including K minus 1. So these were all the entries we saw, excluding row K and so on. So if that's the case, then we're going to define all of the things in the row, all of these elements to be exactly those going forward. So we get, for SK, we have SK plus TK minus 1. And this will be the label for that entry. And then, so this will be +1 for SK. And by SK, I mean the entry associated with SK. So I mean M of KSK. So in particular, we're going to want to remember the KSK part. So you could think of, really what we're saying is L1 is the pair 1, S1, and then we keep going like this. And so at the very end, we'll have L of Tn is exactly N Ln minus 1. So essentially, we're going to do the same algorithm. After we've computed all the SKs and LKs, we can just compute this labeling and then use the uniform random generator to get one of the numbers 1 through Tn. And then we plug the number 1 through Tn into our labeling L to get out the actual pair of ij, which is the row column. So overall, we're going to output ij, which describes the row and column, which is exactly the entry of M picked through this association. So that'll give us exactly what we want for this.